Welcome everyone to this video. It's the first part of a series on stress transformation. So we learned in a previous lesson how to calculate the stress on an inclined or angled cut of that axially loaded beam or axially loaded member. And that was a case to show you that even if we have this cut here perpendicular to this axially loaded member, here we have only axial loads or normal stresses. But when you cut with 45 degrees, you start seeing shear stresses. So that was an example early in this course on generally that your cut affects the generated stresses on such a cut. So if the stresses changes by the orientation of the cut or the section you make, so the question is, where is really now the orientation that gives you maximum shear and maximum normal stress? So what we'll do is we'll analyze now that relationship, like making a formula for stresses as a function of the orientation of the cuts we make. So the general case here we have of, or general state of stresses, we have this 3D stress block, and the stress here occurs at all directions, normal stresses and also shear stresses. But for the sake of our here introductory class to strength of materials, we are analyzing 2D stress state of stresses. So this means that we're analyzing the X and Y only plane of stresses. So no actions happen in the Z direction, so sigma Z is equal to 0. And also the shear stresses in the YZ plane or the XZ plane are ignored. So tau XZ, tau ZY are equal to 0. And that's the case when you have like when we analyze beams in their own plane. Or also in like thin-walled pressure vessels. So you have only 2D stresses on the surface of these vessels. So it's very common to do only 2D state of stresses. And as a reminder, this is the sign convention here that we used. Of course, tension is positive, compression is negative for normal stresses. Maybe the confusing part is the shear stress. We said this is a positive case of shear stress because these two here kind of combined forces that result in is pushing or pulling this square in the direction of the positive quadrant here, so kind of stretching it this way. And negative is the opposite direction. So let's stick to that example here. Let's say that I cut perpendicular, and that represents this cube here, and I can find the stresses if I do this cut perpendicular here and represent the stresses on that cut and the corresponding cube, or in this case square. So I find sigma x, tau xy, sigma y, and the question is, what would be the values of these stresses when I cut not perpendicular here but with an angle of theta. So if you look at this block here, and we're all trying to figure out the values of stresses when I change my orientation by theta degrees. So what we'll do is we'll analyze here, like we'll literally cut this block or cube, or in this case square, with this angled cut. And what we'll see what will be the equilibrium between the new stresses on that cut and the existing stresses on the square that they already had before. So we'll not go into the derivation and the formulas of statics and equilibrium of that free body diagram, if we can say. But if you go to the textbook, whatever textbook you refer to, I'm referring here to Bears and Johnson textbook. In that section, and if you follow the derivation all the way to the end, now you will find that I can relate normal stresses sigma x prime and then sigma y prime, and also the shear stresses tau x prime y prime at any angle theta to a set of stresses sigma x, sigma y, and tau xy. at theta is equal to 0. So theta is relative to the orientation that I had originally that gave me sigma x, sigma y, and tau xy. And now at any angle theta, I can figure out the new values over the transformed stresses on that orientation. So if I'm given sigma x, sigma y, and tau xy either from statics or from lab, when you do strain gauges there and you measure values, I can transform the stresses and find the stresses at any orientation theta from this point. So let's see this example here applying these transformation stress formulas. So we have here this stress block and given sigma x, sigma y, and tau xy. Just to confirm here, tau xy is equal to negative. It's going this way here, squeezing this block along this line here, going through the first quadrant of the axes. And we need to find sigma x prime, y prime, and tau xy, y prime, y prime at 15 degrees clockwise. So if we go to solution here, so we're given that theta is equal to 15 degrees clockwise, and what we'll do is say that theta is equal to negative 15 degrees because my positive is counterclockwise, so that's a negative angle, and this means that my new block of stresses will be like this purple one. And in the formulas, you've seen that the formulas, they are using 2 theta, not theta. So I'm kind of, for simplicity here, calculating 2 theta to be equal to just making it a value ready to plug in the formulas we will have. So here, the theta x prime, if I use the formula and plug in the values here, so 27, and you see here sigma y is plugged in with the sign, and also tau xy is plugged in with its sign, and I end up here with sigma x prime to be equal to positive 31.2 megapascals. So the new block at this orientation of 15 degrees counterclockwise, at 15 degrees clockwise, will feel positive direction, positive stress or tension stress at its own x axis, or in this case x prime. So if I draw here the block, and it's now this face here to the right, the green block was x-axis in the original orientation. Now when in the orientation happens, I can trace that x face of the block, and I draw now sigma x prime on it, and that's the value that I ended up with. Next is sigma y prime, and this is the formula I've seen in the slides. So you just plug in the values. You can see here that it's the same formula almost, but then you're just flipping the signs between the different terms. And you will end up with sigma y is equal to negative 49.2. So now you're having a compression, which means that I increase from 45 megapascal in the original orientation to be 49.2 megapascal compression on that face with this orientation. The last step is figuring out tau x prime, y prime. And that's the formula for it. So you plug in the values, and you will find that your tau x prime, y prime is equal to positive 2.4 megapascal. So my original tau was negative 18. Now it turned out to be positive 2.41. So you'll find that tau in the rotated block will be opposite to the one given to us. And its value is equal to 2.41 megapascal. So that's the end of it. We got all the transform stresses, and kind of it will help you to understand more the answer you got by drawing the block of the transform stresses. That's also a good way of communicating the answer here. So that's the end of this video. It's only like an intro to that series on transforming stresses. We'll see in the next videos the amazing relationship that we have, what we can represent using a circle, which we call Mohr circle, and it will help us a lot in simplifying the solution in these problems. All right, take care. Hisham is out, and peace.